Alright, so in today's tutorials, we want to look at some statistical methods for analyzing one sample data. And before we proceed, I'll urge you to kindly watch my previous tutorial on the flowchart for classifying data, okay? Because in that video tutorial, I have illustrated and explained the data structure for one sample data. So I'll urge you to watch that before you jump into this so that you can catch up with everything that I'm going to do in this video tutorial, okay? So generally, anytime you have one sample data, there are two statistical methods that you can actually use to analyze such a data. We have the parametric test and we have the non-parametric test. The parametric tests are statistical tests for population parameters such as the mean, based on the assumption that the population from which the samples are selected follow a normal distribution, right? And the non-parametric test, on the other hand, are statistical tests for population parameters such as the median that is not based on the assumption that the population from which the samples are selected will follow a normal distribution. Okay, so the type of parametric test that we often use for analyzing one sample data is called a t-test or the one sample t-test, and the non-parametric test used to analyze one sample data is called a sign test or the quantile test. Okay, so let's look at the parametric test for one sample data, that is a one sample t-test. The one sample t-test is a statistical hypothesis test used to determine whether the unknown population mean is different from a specific value. Okay, so for example, we might want to know if the mean waiting time in a doctor's office is greater than 1 hour, or if the mean growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. There are some assumptions that must be satisfied before we make use of this test. So one of the assumptions is that data must be continuous and the data must be normally distributed. Okay, now let's look at the case of non-parametric test for one sample data, that is the sign test or the quantile test. The sign test is a statistical hypothesis test used to determine whether an unknown population median is different from a specific value. Okay, so here the population parameter that we are focusing on is the median instead of the mean. Okay, so for example, we might want to know if the median waiting time in a doctor's office is greater than 1 hour, or if the median growth of roses is 4 inches or more after 2 weeks of treatment with a certain fertilizer. Here we have some conditions that must be satisfied before we make use of this test. One of the conditions is that data must be continuous and the data must not be normally distributed. Okay, so let's look at an example. So using the iris data set, as a researcher, you wish to test whether the average length of the sepal from the iris data set is different from 6 centimeters. Perform a statistical analysis for this data, and we are going to analyze this data in R. Okay, but before we proceed, let's look at the iris data set in the CSV format. So this is the iris data set. We have assumed we have already passed through the data cleaning or the data preparation stage. So this is a clean data. I'm going to leave this data file in the description of the video so that you can download it. Okay, so this is a clean data. We have already cleaned it, even though we have to adopt some data manipulation technique before we analyze our data. So the questions want us to basically determine if the average length of the sepal is different from 6 centimeters, but you have to be very careful if you want to analyze this data, because the sepal length was taken for 3 different groups of the species. We have one for Setosa, we have one for Versicolor, and we have one for Virginica. So if you just use the whole of the sepal length variable in your analysis, you may end up doing a wrong thing. For instance, if you just use the whole of this in doing your t-test or your sign test, you may end up doing different thing altogether. Okay, you have to first of all filter the sepal length for Setosa, and filter the sepal length for Versicolor, and filter the sepal length for Virginica. Then you perform a t-test or a sign test on each one of them. Okay, so that's what we are going to do. So let's quickly jump into R. Alright, so first of all, we would like to clear all our working environment and graphics. So if you already have something clean like mine, you can skip this and go straight ahead to import your data set. Okay, so I want to assign my data to IDAT, my data set to IDAT, and I'm using the read.csv because the file has a CSV extension, and I'm using the file that choose to basically choose from the folder where I have my data file. So let's quickly run this. Alright, so let me navigate to the folder where I have my data file. So desktop, let me scroll down. YouTube tutorials. So one sample data. So this is my data file. So let me click on this. Okay, so once you import it, you will see an information of it in the environment window. So you can either run this to view the data set in a spreadsheet form, or you can click on this to view your data set. So let me click on this. Alright, so here we go. Alright, so that is the iris data set. Okay, so let's go back to our script file. So now I want to look at the structure of our data set. So let's highlight this and run. We can see that the data type for Sepal length, Sepal width, petal length, and petal width, they are all numeric, right? But species is string, right? So in our data manipulation, we are supposed to encode this. We are supposed to convert the string to numeric, or we are supposed to assign some values to these labels, okay? Before we can use it in our analysis. So let's quickly do that. So in our data manipulation, basically we would like to make use of the dplayer library. Okay, this will help us in our data manipulation. So let's quickly run this. If you don't have this installed, you can go to packages and click on install and type the name of this to install. Okay, I already have this, so I can basically skip the installation and just load the library. So let me run this. Okay, so once we have loaded our library, we can then do the encoding. So I want to recode a species from string to numeric. So I'm assigning everything to new dat. So for my IDAT, I'm using the forward pipe operator, which basically passes the left hand side of the operator to the first argument on the right hand side. So basically what I'm trying to say is that for my IDAT, right, my imported data, I want to basically convert the species to from string to numeric, or basically to assign some values to the labels. Okay, but I don't want to use the original name of the species so that it will overwrite it. Okay, if I just use species, it will overwrite this one, so I just want to use species one so that I can have a new variable. The mutate function basically adds new variable and preserve existing one. So we are going to add a new variable to our current data set. Let's quickly run this. Let me highlight. Okay, so let's run this. Okay, so let's look at the structure for our new data set now. So we have seen that now we have assigned some values to the labels, so we can actually make use of this. So we can actually even remove this because we don't need this, right? And we can even rename our data set if we wish to. We can also click on this to view our new data set. Okay, so we don't need this, but we need this. Okay, we can even rename these variables. So let's quickly do that. So I want to remove and rename some variables. Let me highlight this. Okay, so for my new data set, I want to basically select the species, but because of the minus sign, I'm not selecting this, rather, but I'm removing this species variable. Then after removing it from my new data set, I want to rename the sepal length as SL, sepal width as SW, petal length as PL, petal width as PW, and species 1 as SP. Okay, so let's quickly run this. Alright, so let's scroll down. Let me use the table function to get the first 10 observations. So let's run this. Let me scroll up. So we can see that we have renamed our variables, right? And we have also removed that string species. variable, and I've maintained the one with a factor. So I think we are good to go. Okay. So now that we are done with this part, we are supposed to filter our data set. Okay, don't forget that we are supposed to determine whether the average length of the sepal length is different from 6 centimeters. But we can't use the whole of this variable. We are supposed to get the sepal length for setosa. So once we filter, we are going to pick from 1 for setosa, 1 to, let's say, let me scroll up, setosa at 49. Then we'll filter that for versicolor, starting from 50, right, row observation 50 to, let's say, yep, 99, right. Then we'll do same for Virginica. We'll filter the sepal length from 63 to, no, from 100 observation, yeah, 100 to 148. Okay, so let's quickly do that. So we want to filter now the species plant of the sepal length. I want to filter the setosa of the sepal length. So I'm assigning everything to G1 underscore SL, which is the group 1 of the sepal length, which is setosa. So from my new data, I want to filter. I'm using the filter function from the dplayer library. So SP is equal to setosa. Okay, then after filtering this species, I want to select the variable sepal length. Okay, so let me highlight this and run. So we can click on this to view the dataset. Right, so let me close this. So let's go back to our script file. So I'm going to do the same for versicolor, filter the versicolor of the sepal length. So new that, and I'm assigning everything to G2 underscore SL. Okay, so filter, and in here I'm using versicolor, and after doing this filtering, I want to select the variable sepal length. So let's run this one. You can also view our data. So here we go. Okay, so let me close this too, and do same for Virginica. Okay, so new that, I'm assigning everything to Gen3 underscore SL, that's the group 3 of the sepal length, which is Virginica. So filter Virginica, right, and select the sepal length. Let's run. So let's click on this. Yep, so you're good to go. So the first one has 49, the second one has 50, and the third one has 49 observations. Okay, so we are good to go. Alright, so once we are done with this, what next? So the next thing that we're going to do now is to basically do some exploratory data analysis. Okay, if you have not watched my previous tutorials on UDA, I'll urge you to kind of go watch that if you want to get more ideas or more insight with regards to UDA. Okay, so in our EDA, we are going to get a summary statistic of the sepal length for setosa. Okay, so in here I'm going to use a summary function to basically get a 5-number summary, which always includes the mean. Okay, and then I'm using the apply function to also get the standard deviation so that we can check the variability in our data set. So the first argument here is our data, and the second argument is the dimension that we are looking at. One is for rows, or the number of rows. Then 2 is for the number of columns, which are the variables. So yeah, I'm dealing with the number of the variables, right? Then the third argument is for the function. So we are interested in standard deviation. So SD is for standard deviation. So let's run this through and see the result. Okay. So we can see that for the 5-number summary, the first item is the minimum value. We have the second item to be the first quartile. We can combine the mean and the median, right, as one. So that's the third item. Then the fourth item is the third quartile. Then we have the last item to be the maximum value. Okay, so in here, the minimum value and the maximum value, we can get a range, right? And the range basically is the overall dispersion of values in our data set. So once we subtract this minimum from the maximum, we get a range, which tells us the total spread of values in our data set. Okay, then the median or the mean basically is telling us the peak where most of the data values are being clustered. Okay, so we can see that they are clustered around 5 centimeters. And if you are to divide our data set into two right? It means that 50% of the values are about 5 centimeters and 50% of the values of the sepal length of the setosa are below 5 centimeters. Okay, then the median of the upper half is given by the third quartile or the 75th percentile. Okay, so here we know that 25% of the values are greater than 5.2 centimeters and 75% of the values are below 5.2 centimeters. Okay, so we can interpret this as let's say the top 25% of the sepal from the setosa plant increases in length than 5.2 centimeters, and the median of the lower half is given by the first quartile or the 25th percentile. Okay, so we can also interpret this as we know that 25% of the values are below 4.8 centimeters and 75% of the values are above 4.8 centimeters. So we can interpret this as a single setosa plant of the sepal chosen at random has a 75% chance of increasing in length than 4.8 centimeters. Okay, so these are some of the descriptive statistics that you're supposed to basically talk about before you start with your main analysis. So it's very important, and you can check the variability of the data set by looking at the standard deviation value here. Okay, so let's do same for the other data. So let's look at the summary statistics of the sepal length for vesicle. Okay, together with the standard deviation. So I'm gonna run this. Okay, so here we go. So you can do the same interpretation for this. Let me do same for the summary statistics of the sepal length for Virginica. So let's run this. Okay, so we get also the summary statistics. Okay, so we can actually visualize this 5-number summary by making use of the box plot. Okay, the box plot is basically a way of displaying the distribution of data based on the 5-number summary. Okay, so let's quickly do that, but before that, let's look at a library that we're going to use for our data visualization, which is the Untitled Plot. If you don't have this installed, you can just go to packages, right, and click on install to install that. Type the name of this to install. Okay, so I'm going to load this library. So let me run this. So I want to get a box plot of the sepal length for setosa. So this is I'm assigning my data graphic to BP1. Okay, so the ginger plot, the first argument is for your data, and the second argument is the static mapping, which is basically you are going to make use of the variables in your data. So yeah, the variable that we have in our data is the sepal length. Then I want to plot a box plot, so I'm using the geom box underscore box plot. Okay, so let's run this. So here we go, we can see the box plot, and we have the first item, that's the minimum value 4.4. This line is going to give us the first quartile or the 25th percentile. This model line here is pointing towards the median value, and this is pointing towards the third quartile or the 75th percentile, and this is pointing towards the maximum value. Okay, so you can basically, this is how you can graphically check your 5-number summary, and you can also get the shape of your distribution by making use of the box plot. Okay, you can see that the length over here from year to year is basically, even though year seems to be slightly greater than year, you can also check this box. You can see that the area on the left hand side is the same as the area on the right hand side, together with the length here, and the length here is slightly greater than the length here. So describing the shape of this distribution, we can say that this is nearly symmetric. Okay, so let's check that of vesicular. So box plot of the sepal length for vesicular. So yeah, I'm assigning everything to BP2 ginger plot. So yeah, G2, that's the data for vesicular, and the variable sepal length. Then you plot your the box plot. Okay, geom box plot. So let's run this. So here we go, we can see that year to the shape of the distribution is nearly symmetric, right? If you look at the distance from year to year, the same as the distance from year to year, and the area on the right hand side seems to be slightly greater than the area on the left hand side. So this can also is an indication that the shape of the distribution is nearly symmetric. Let's get that of Virginica, the box plot of the Sepal length for Virginica. So yeah, BP3, Gen3, and Excel, that is variable. So let's run this. Okay, so here we can see that we have some extreme values, right? Now, having some extreme values does not necessarily mean that they're outliers. You have to be very careful when you're dealing with outliers. If you want to get more information with regards to outliers, you can also watch my EDA tutorial in R. Okay, so you can see that the distance from the minimum to the first quartile, the same is that from the third quartile to the maximum value. Okay, but just that the area on the right hand side seems to be greater than the area on the left hand side in the box. So this is also an indication of nearly symmetric. Okay, even though it seems to be skewed to the right by seeing. Okay, so sometimes the shape of the distribution may be something that you would like to get some other statistics to describe the shape of a distribution, like computing for the skewness and ketosis. We know that skewness is a measure that describes the degree and direction of departure from symmetry, right? A distribution is said to be symmetric if it has the same shape on either side of the center value, right? And ketosis basically describe the peakness, right, of the curve, right? If you want to look at the peakness in our curve or look at how heavy or light the taste of the distribution is in comparison to that of normal, then we make use of the ketosis, right? So to get more information with regards to skewness and ketosis, the box plots may not reveal much, even though we have seen some clear indication. Let's compute that of the skewness and ketosis. So in order to do that, we need to make use of the library known as the moment, okay, to compute for skewness and ketosis. So let me run this. So if you don't have this installed, I have to go to packages and click on install to install. Okay, type the name of this. So let's get the skewness of the Sepal length for Sentosa. So use the skewness, then we pick the variable from the data, we pick the variable Sepal length. So let's run this. So the skewness is 0.190 from literature. If the skewness is around minus 0.5 and plus 0.5, then it means that the distribution is nearly symmetric, right? But if the skewness is greater than 1, or let's say it's less than minus 1, then the distribution is said to be highly skewed. So looking at this, is within 0.5, so we can say that um, our data is nearly symmetric. So if we go back, let me go back to that of the Sepal length. This is for the first one, so we can indicate that this is nearly symmetric, right? Let's look at that of the second one. That is the skewness of the Sepal length for versicolor. So once we run it, this is also within 0.5, so this is also nearly symmetric. So from the box plot together with the skewness coefficient, we can confirm that the Sepal length for versicolor is also nearly symmetric, right? Let's check that of Virginica, skewness of the Sepal length for Virginica, right? So let's run this. So we have, this is also nearly symmetric, right? If we check that of the box plot, you can see that this is an indication that it is nearly symmetric, right? So now let's get that of the ketosis. Alright, so in here we're making use of the SS ketosis. The SS ketosis is used in comparing the ketosis coefficient, right, with that of the normal distribution. And we get the SS ketosis by subtracting 3 from the ketosis coefficients, right? So when the SS ketosis is approximately equal to 0, then we say that the distribution is mesochaotic, which means that it is the peakness in a curve, or the peakness of the distribution is normal in shape. And if the ketosis is less than, the SS ketosis is less than 0, then it means that the peakness, right, in a curve, or the peakness of the distribution is plateautic, right? And if the SS ketosis is greater than 0, then we know that the peakness of the distribution is leptochaotic, which means that let's say the tails of the distribution is, or the peakness in the distribution is higher than 10, right? So let's quickly run this to see the SS ketosis. So yeah, it's less than 0, right? That's the SS ketosis, so the sepal length for setosa is less than 0. So this is an indication that the this indication that we have a plateautic distribution, which means that the peakness of the distribution is flat and spread out, or the tails of the distribution is flat and spread out. Okay, so let's look at that of the SS ketosis of the sepal length for versicolor. So let's run this. This is also less than 0, so this is also said to be plateautic. Let's check that of the Virginica. So once we run this, this is also less than 0, so they are all plateautic. If you want to get more information with regard to the Qns and Ketosis, we can plot the histogram for each one of them. So histogram plot. So we want to get a histogram plot of the sepal length for setosa, right? So let me highlight this. Alright, so in the first argument, code of line, I want to basically, I'm assigning my data graphic to H1. So that is the data for sepal length for setosa, and the variable is the sepal length. And I want to plot a histogram, right? So on the y-axis, I'm not interested in the frequency, I'm interested in the density, so I'm using density. Then the bins, I'm setting this to 10, right? We know that with the bins, it represents a range of values, right? It's a single bar. Okay, the bin is basically a single bar which represents a range of values, and the height of the bar represents how many data points fall into that range. Okay, so you can change this. Then we want to fill each bar with the color sign. Then we want to color the border of our bars with blue. We also need a geom density. We want to put the density within our histogram so that we can basically check for the ketosis. Then we also want to get the mean value for the sepal length in our histogram so that we can basically check for our skewness. Okay, we know that a distribution is said to be symmetric if we have the same shape on either side of the center value. So once we have the mean value, we can check for the skewness. We want to color this mean value with red. Then we also want to add some labels. So I want to give a title, histogram plot of the sepal length. Right, let's see the other end. Histogram plot of the sepal length for setosa. Right, and our X label we want to use sepal length. So let's quickly run this. I'm going to highlight and run. Alright, so here we go. So if this is my center value, if you look at the rate on the left hand side and the weight on the right hand side, they are almost the same. So this is nearly symmetric. Now from the density that we have, the density curve in our histogram plot is also an indication that this is the distribution is plateautic, which means that the peakiness of the distribution is flat and spread out. Okay, now let's check that for the histogram plot of the sepal length for versicolor. So I'm going to highlight this. Okay, so yeah, I'm assigning everything to H2, the data for versicolor, the variable sepal length, then everything as it goes. So let's run this. So in here, if this is my center or the middle value, if you look at the weight on the left hand side and the weight on the right hand side, they are almost the same, so you can say this is nearly symmetric. And if I'm checking for the ketosis, the density plot is, if you look at the tails of the distribution, it is flat and spread out, so this is an indication that we have a plateautic distribution. Okay, let's check for that of Virginica, histogram plot of the sepal length for Virginica. I'm going to highlight everything. So I'm assigning everything to H3. That's my data for Virginica. The variable of interest is sepal length. Then everything follows like the first one. Okay, so let's run this. Okay, so if my middle value is here, if you look at the weight here and the weight on the right hand side, you can see that this one is nearly symmetric. If you check for the density within the histogram, you can see that the tiers of the distribution is flat and spread out. So this is a typical example of a Plateautic distribution. Okay, so we are good to go. So once we are done with this descriptive statistics, then we can proceed to test for the assumptions to find out if we can make use of the t-test or the sign test. So from the indication that we have from our expiratory data analysis, we can see that most the data that we have, right, the data for Sepal length of Setosa, that of Vesicala, and that of Virginica, we can see that we have an indication that they may satisfy the normality assumption. Okay, but we have to test. So let's check. We want to test for the normality assumption. We are going to make use of the QQ plot. Okay, this is just one test that we can make use of. We'll be making use of the other test, that is the Shapiro and the Anderson-Darling test. So with a QQ plot, we need a library known as the QQ plot R. Okay, so let's run this. If you don't have this installed, you can go to packages and install. So I want to get a QQ plot with a Sepal length for Setosa. Okay, so with a QQ plot, it basically draws the correlation between a given sample and the normal distribution. Okay, so if a data is approximately normal, then the plot will closely resemble a straight line sloping upward to the right. So let me highlight this. We are going to get a QQ plot of the Sepal length for Setosa. Okay, so in here, my data for the QQ plot, my graphic data is going to be QP1, and the variable of interest, that's the sample, is the Sepal length. Then I want to get the QQ band, that's the confidence band. Then the QQ line. Okay, this line will help us to know whether all the points follow closely or resemble a straight line sloping upward to the right. Then we need a point. Then we also have to give some labels. So the x-axis are my theoretical quantiles, my y-axis are the sample quantiles. Okay, and the y-axis are the sample quantiles. Then the title QQ plot of the Sepal length for Setosa. So let's quickly run this. Okay, so once we run this, let's see the result. So we can see that most of the points are within the confidence band, and we can see that the plot resemble a straight line sloping upward to the right. Okay, so this is an indication that the data of the Sepal length for Setosa follow the normal distribution. Okay, so this is an indication that we can even make use of the t-test. Okay, let's check that of the QQ plot of the Sepal length for Vesicala. So I'm going to highlight this. Okay, so now my data, my graphic data is QP2, my data is G2, that's the data for Sepal length, right, of the Vesicala. Then the variable is Sepal length, so the confidence bound, QQ line, QQ point, and this are my title, right? So let me run this. In here too, we can see that most of the points are within the confidence bound, and the plot also resembles a close line sloping upward to the right. So this is an indication that the data of the Sepal length for Vesicala is normally distributed. So this is also an indication that we can make use of the t-test. Okay, let's check for that of Virginica. Okay, so my graphic data is QP3, right, data for Virginica, Sepal lengths, right. So let's run this. In here we can see that some points seems to deviate. They are not within the confidence bound, even though majority of the points are within the confidence bound, and there's plot also resemble a close line sloping upward to the right. So I think we are good to go. So in order to even confirm whether what you have follow normality, it is advisable not to use only one test. So that is why I indicated the first one to be 1. So that is for QQ plot. We can also make use of other tests to confirm this graphical graphical output. So we have other tests for normality, which are the Shapiro-Wilk test and the Anderson-Darling test. Okay, this test has the null hypothesis that a distribution follow normality. Okay, so before we make use of this test, we need a library known as the north test library. So this library is basically for the Anderson-Darling test. So I'm going to load this. If you don't have this installed, you can go to packages and install. Okay, so I'm going to run this. Okay, so let's look at the Shapiro test and the Anderson-Darling test of the Sepal length for Setosa. So let me run this. So let me scroll up. So there's a Shapiro-Wilk test. We have p-value of 0.325, which is insignificant, right? So we fail to reject the null hypothesis and conclude that the data, right, of the Sepal length for Setosa follow normality, or is approximately normally distributed. The same applies with that of the Anderson-Darling test. We also have an insignificant value of 0.2879 in comparison to a significant value of, let's say, 0.05. We fail to reject the null hypothesis and conclude that the data of the Sepal length for Setosa is approximately normally distributed. Okay, so this is an indication that we can basically use the t-test for the Sepal length for Setosa. Okay, let's check for that of vesicular. So we want to look at the Shapiro-Wilk test and the Anderson-Darling test of the Sepal length for vesicular. So let me run this. So in year 2 we have an insignificant value, right, 0.4647. The same applies to that of the Anderson-Darling test. We have 0.433. So here we fail to reject the null hypothesis and conclude that the data of the Sepal length for vesicular also satisfy the normality assumption. Let's check for that of Virginica. Okay, so let me run this. So in year 2 we have an insignificant value of 0.2533, and in year 2 we have 0.136 in comparison to a level of significance of 0.05. So we fail to reject the null hypothesis and conclude that the data of the Sepal length for Virginica also satisfy the normality assumption. Okay, so I think we are now good to go. Right, so once we are done with this, we are now clear with the kind of statistical technique we are going to use. So this is an indication that we are going to make use of a parametric test, that is the one sample t-test. Okay, so the null hypothesis is that the average value of the Sepal length is equal to 6, and the alternative hypothesis is that the average value of the Sepal length is different from 6. Okay, now I want to clear something before we proceed. In books, you realize that we always come across this statement that we can make use of the t-test once the sample size is less than 30. Okay, but in reality we can make use of the t-test even if the sample size is more than 30. Okay, the reason being that the t-test is actually a symmetric distribution like the normal distribution. The difference is that the t-test has a variance that is greater than 1, and the t-test is actually it's a family of curves that is based on the concept of degrees of freedom. Okay, so and this degrees of freedom is related to the sample size. So as the sample size increases, the t-test actually approaches the standard normal distribution. Okay, so even if you have a sample size that is greater than 30, we can actually make use of the t-distribution. Okay, so now let's proceed to the t-test of the Sepal length for Setosa. So I'm going to say t.test, that's the function, and that's the data for Setosa, and I'm interested in the variable, so I'm using $sign to pick that variable. Then the hypothesized value was 6, right? And the alternative is going to be two-sided. Okay, we are saying it's different from 6. So let's run this to see the output. So in here, the test statistic result is what we have here. The degrees of freedom is 48, and the p-value in comparison to a significant value of 0.01. It means that we have a significant result, right? So here we reject the null hypothesis and conclude that the average value of the sepal length, right, of the sepal length for setosa is different from 6, right? Now, if you check the mean value for sepal length of the setosa is 5.0, so in comparison to the hypothesis value, you can see that there's a gap. Okay, there's a clear difference. So we are good to go. Now let's check the t-test of the sepal length for versicolor. So in here, t-test, my data for versicolor is G2SL, the variable is sepal length, hypothesis value is 6, right? Two-sided, that's the alternative hypothesis. So let's run this to see the result. The test statistic is minus 0.87, degrees of freedom is 49, right? Now the p-value here is 0.3849 in comparison to, let's say, an alpha value of 0.05. We failed to reject the null hypothesis, right? And conclude that the average value of the sepal length for versicolor is not different from 6, right? Now if you look at the mean value is 5.9. In comparison to the hypothesis value, we can see that it's not all that different. That is why I think we are failing to reject the null hypothesis and conclude that the average value of the sepal length for versicolor is not different from 6. Okay, so let's check for that of Virginica. So t-test of the sepal length for Virginica. So that's the data for Virginica. Sepal length is the variable. Then my hypothesis value is 6, alternative two-sided. So let's run this. In here, the test statistic is what we have here. Degrees of freedom, p-value is less than 0.05 if you compare this to an alpha value of 0.01, right? So we reject the null hypothesis, right, and conclude that the average value of the sepal length for Virginica is different from 6. Now if you look at the mean value for the sepal length for Virginica, we can see that is 6.6, which is far different from what we have here. So I'm not surprised with the conclusion that we are trying to draw. Okay, so I think we are good to go. Now let's assume the normality assumption wasn't satisfied. Okay, then we are supposed to make use of the nonparametric test. Okay, so in the nonparametric test, you are going to make use of the sign test or the quantile test, but we need a library known as the BSDA library. This will help us to do the sign test. So assuming the normality assumption wasn't satisfied, then we are going to make use of this test. Okay, so let me run this library. If you don't have this installed, you can go to packages and install it. So with this, I'm going to get a sign test of the sepal length for setosa. So this is the function sign.test. Then in here is my data for setosa, the variable sepal length. So in here we assume the average value is a median. So that's the hypothesized value is a median value 6. Alternative is two-sided. Let's run this to see if you're going to draw the same conclusion. Let me scroll up. So we have a significant result, 0.0 is less than 0.01, right, in comparison to alpha value of 0.01. So here too we conclude that we are going to reject the null hypothesis, right, and conclude that the average value of the sepal length for setosa is different from 6. Now the median value is 5 in comparison to 6. So I think the conclusion makes sense. Let's check for that of the sign test of the sepal length for versicolor. So let's run this. So let me scroll up. So what do we see? In here we also have an insignificant value in comparison to an alpha value of 0.05, right? So in here we fail to reject the null hypothesis and conclude that the average value of the sepal length for versicolor is not different from 6. Okay, the median value is around 5.9, which is from the hypothesis value, they're almost the same. So that's why we are drawing the same conclusion. So we can see that even with a parametric test, we are drawing the same conclusion. Okay. So let's check for that of the Virginica. So the sign test of the Sepal length for Virginica. So the data for Virginica, Sepal length, median value, hypothesis value, alternatives two-sided. Let's run this. Let me scroll up. So in here to the p-value in comparison to an alpha value of 0.05 or 0.01, we reject the null hypothesis and conclude that the average value of the Sepal length for Virginica is different from 6. Now the median value is 6.5 in comparison to this. There's a clear difference, okay? So I think we are good to go. So this is basically how to do this, perform some statistical analysis for one sample data in R. Please, if you find value in this tutorial video, don't forget to subscribe if you have not, and also click on the notification bell to get more updates anytime I post on this channel. Thank you for watching.